Okay, the next thing we're going to talk about is the next tool, which is called the upper and lower bound rule tool. And we use this upper and lower bound tool with synthetic division. And what this does, it takes all of the possible roots that you had in your from your rational root test. We take all of the possible roots that were shaved down, cut down by the Descartes rule of sign tool, and the upper and lower bound rule, together with synthetic division, takes those leftover numbers and chops them down further, chops down the list of possible roots further down. And here's how it works. Let's say you're doing your synthetic division, and x. Let's say x is equal to a positive number, right? X equals a positive 2, and you get a remainder. It's not 0, right? And all the numbers that come out are positive. If that's the case, that's going to be an upper boundary, right? If you're dividing by, let's say x is equal to a negative number, like say a negative 2, okay, and out comes the answer that comes out are alternating positive and negative numbers, or negative and positive, right? Numbers. It doesn't have to be in any particular way. It can be positive, negative, or negative, positive, negative, positive, positive, negative, right? If you see that, right, and they're alternating, and this is going to be a lower band, right? Roots are in between upper and lower bands. If you reach a higher upper band, you can't go any higher. It makes no sense of going any higher when you reach that upper band. And if you reach a lower band, it makes no sense of going any lower. Go up, and so that you will find that root that you need. Okay, let's do an example. Let's say we have f at x is equal to x to the 4th power plus x cubed minus 26x squared plus 24x. Well, let's determine if x is equal to positive 6 is an upper band of this function. So the first thing we got to do, we're going to test is x equals to positive 6. The first thing we're going to do, look at the function, right? The first thing we must do is factor. Look at it. We have to factor everything. So our common factors are x. And so we're going to factor out the x. Okay, let's factor it. Okay, factor out x. Good. So now we've factored our x. Now we're going to take this number in this function in between the parentheses, and we're going to factor it. We're going to test for x for this function in between the parentheses. That's x equals a 6 to see if it's an upper boundary. Okay, let's try it. Let's do our synthetic division. Okay, test x equals to 6. Okay, 6. We're gonna put an L-shaped thingy. And we're going to make sure our powers are arranged in descending order: 3, 2, 1, great, 0, excellent. So 3, our coefficient is 1, negative 26, and 24. 24 is the remainder number, so I like putting the little dot here to express that. Okay, bring down our 1, and 1 times 6 is 6. 6 plus 1 is 7. 7 times 6 is 42. 42 minus negative 26. 42 plus negative 26 is 16. 16 times 6 is 96. 96 plus 24 is 120. Now, since our remainder is not 0, x equals to 6 is not a root. But look, you can use this. We still can use this to our advantage. Look, the answers are all positive, so it's an all positive boundary, and this is the upper boundary. So if you see this, then when if x is equal to a positive number, and the answer comes out with all the answers are all positive, this is called the upper boundary, or upper bound in some textbooks. I like saying upper boundary, right? Upper B. And once you have an upper boundary, you don't need to go any higher. It makes no sense of going any higher than that. You go lower. You look for all the numbers. You test all the numbers that are less than that. Okay, so let's try to test for if x equal to 8, negative 8, x equals to negative 8. Let's try to test if that is a lower boundary. Okay, we got 1, negative 26, 24, okay. Okay, bring down our 1. 1 times negative 8 is negative 8. 8 plus 1 is negative 7. Negative 7 times negative 8 is 56. 56 plus negative 26 is 30. 30 times negative 8 is 240. Negative 240. Yeah. Okay, so the answer is going to be negative 240 plus 24 is negative 260. 16. Negative 216. So it's not a root, right? X equals to negative 8 is not a root because our remainder is not 0. But look, we see that it's not a root, right? It's not a root. We look at the answer. It's alternating between positive, negative, and positive, and negative. You see that? So this is going to be a lower boundary. That there's no need to go any lower than this. That's all. So we're not going to go to for this function. The lowest number we had was negative 24. You know, for this particular function, right? So we don't need to go any lower than that. We already went to the lowest boundary, which is negative 8. So we're gonna go higher than 8. We're gonna look at other things like we saw before, like negative 6 or negative 4, negative 3 or negative 2 or 1, you know, to find the roots of this particular function. So that's basically the concept of what an upper and lower boundary is. Okay, so we're going to put all of our tools together that we learned so far in solving non-factorable or hard to factor polynomial functions. So we previously learned about the upper and lower bound rule with synthetic division. When we had an upper boundary here, we went lower. When we had a lower boundary, we went higher. With upper boundaries, we'll have a positive x equals to a positive number. We'll put that as a divisor, and we will use synthetic division. And when we come out with our remainder, our answer, if all of them are positive, then that's an upper bound. A lower bound, if we have x equals to a negative number, we put that divisor into the function, and we come out with alternating signs, positive, negative, or negative, positive, then that negative number, that negative divisor, and the answer, that will be the lower boundary. And in between, so we will go up. So in between the upper and lower boundary will exist a root somewhere. Okay? So let's put that together with the rational root test, Descartes' rule of signs, and one last thing to keep in mind is that when we find the root after we combine these tools together, we're gonna apply the shortcut until we get to the quadratic level. So if we're at a power of 5, we're gonna apply the shortcut to get to a power of 4, then apply the shortcut again, find roots and apply the shortcut again to get down to a power of 3. And then when we get down to the power of 2, which is the quadratic level, we stop there. And we do one of two things. We can either factor, and if we can't factor, we can use the quadratic formula in order to find the last 2 missing roots. So let's get going. Okay, now this is going to be one of the hardest things that you can factor. And if you can master this, you're gonna be amazing at polynomial, finding the zeros of polynomial functions. Okay, so in order to get the rational root test, in order to get the in order to start, we're still going to start with our in order to get to the zeros of the polynomial functions, the first thing we need to do is find we need to use the rational root test. Now, the rational root test will give us a list of all the possible roots that there might be for any given polynomial. Okay, so here's how it works. We're going to get the factors of the constant, and you got to remember, before we even get the factors of the constant or the factors of a leading coefficient, right? We have to make sure that our polynomial, our function, is in descending order of powers. So we should have 4, 3, x 2, 1, 0. It's assumed that you already know that this is to the power of 0. Anything to the power of 0 is equal to 1. 128 times 1 is 128. So it's a constant. Okay? So factors of the constant, which is here, and factors of a leading coefficient, which is here. Leading coefficient is an invisible 1. Okay? So, our rational root test, factors of the constant, factors, I'll put F, factors of 128 over factors of 1. No. What are the factors of 128? Well, we have positive and negative 1, positive and negative 2, positive negative 4, positive negative 8, positive negative 16, positive negative 32, positive negative 64, or positive negative 128. And the factors of 1 are positive negative 1. Anything divided by 1 is itself. So we're going to just, are the roots that we're going to have, are the possible roots that we're going to have are these numbers. And we have how many numbers? 1, 2, 3, 4, 5, 6, 7, 8 times 2. So we're going to have 16 possible roots that we have to test. That's a lot of roots. So in order to shave it down, we're going to use the Descartes rule of sign tool. And when the Descartes rule of sign tool again is when we have so many possible roots, this tool cuts down all the possible more possible roots, and it tells us whether to start positive or negative. Okay, so let's use the Descartes rule of sign tool, and I'm going to bring in our chart here. Okay, here we go. Okay, first with the Descartes rule of sign tool, we have to find f at x, the signs of f of x and the signs of f at negative x. So first let me put in f at x. It's x to the 4th power minus 10x cubed plus 24 x squared plus 32 x to the 1st power minus 128. Okay. And the signs of f at x are positive. Right? F at x. The signs are positive, negative, positive, positive, negative, positive, negative, positive, positive, negative. Okay. The number of sign changes are, let's see, positive changes. 1, 2, 3. 3 sign changes from positive to negative. So the number of real roots are 3. And remember our rule, or according to the rule, we're going to have the number of sign changes minus an even integer. And so it's going to be 3 minus 2. 2 is an even integer. So the number of real roots, we're going to have a 3 or 1 positive. Okay. Now we're going to do this function, f at negative x. So we're going to change all the x's into negatives and see what comes out. If we put a negative inside here, x to the 4th power, right? It's going to come out positive, right? Anything to the power, an even power, is going to be positive. So we're going to have this. If we put a negative here, anything to an odd number, if we put a negative here, it's going to become, this sign is going to change. Okay, it's going to be positive 10x cubed. This is even, it's going to stay the same. If we put a negative inside x, that's odd, so it's going to, the sign, this positive number, if we multiply it, will change to negative. Okay, and there's no x here, so it stays the same. Okay, so that's the function at negative x. So we have positive, 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 negative, negative. Positive, 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 negative, negative. How many sign changes do we have? We have 1 sign change. From positive to negative, it doesn't change again. 1 sign change. So the number of roots are 1. 1, negative. Okay? Now, the cases that we have are, case number 1, we have 3 positive roots and 1 negative real root. We have a total of, we have a power of 4, so we're going to have 4 solutions. 3 plus 1 is 4, so we have 0 complex roots, total of 4. Case number 2. We have 1 positive and 1 negative. Okay. And we have 2, 1, 2. The number of the highest power is 4. So the number of solutions we should have are 4 solutions. So 1 plus 1 is 2. Complex numbers, we add to that. You should have two complex numbers. Total of this should be 4. Okay. Now, if we look at the column, the positive columns and the negative columns, we're going to find out which scenario we should, which column we should follow after, positive or negative. Which ones will be the best one to go after. And for me, I personally feel that the positive column will be the best to go after. All the positive possible roots, because we're guaranteed 3 or 1 roots. With the negative column, if we go after the negative numbers, we're only guaranteed 1 root, 1 or 1 roots. So this is the best. This is more efficient to go after all the positive numbers, and that's what we're going to do now. Okay. So let me move this out the way. So we had before, how many numbers did we have? 16? I think we had 16 numbers. So if we're going to go after only the positive roots, half of the possible roots will be shaved down to only 8 roots. So we're going to have, now the possible roots will just be plus 1, 2, 4, 8, that's 3, 4, 8, 16, 32, 64, 128. These are all the possible roots that we are going to have here, and guess what? We have to test them all to find out which ones are the roots. And we're going to apply upper and lower bounding rules within synthetic division in order to get at the root. The upper bounds will tell us to go lower. The lower bounds will tell us to go higher. So let's first test. Let's test x equals to 1. Okay, test x equals to 1. Okay, and we get our put a little 1 here, L-shaped thing here. Put in the coefficients of 1, negative 10, 24, 32, and negative 128. That last number will be our remainder, right? That's r at x. This thing is our f function. This is our divisor. Okay. Now bring down our 1. Now multiply 1 times 1 is 1. Negative 10 plus 1 is negative 9. Negative 9 times 1 is negative 9. 24 minus 9 is 15. 15 times 1 is 15. 32 plus 15 is 47. 47 times 1 is 47. Negative 128 plus 47 is negative 81. Oh, well, since this remainder is not 0, this test fails, and x equals to 1 is not a root. Okay, let's test for x equals to 2. Okay. We have 1, negative 10, 24, 32, negative 1, 128. Okay. Bring down the 1. 1 times 2 is 2. Negative 10 plus 2 is negative 8. 16. 16, 48. 48 times 2 is 96. And the answer is 32. So this test fails. Okay, so it's not, root is not x equals to 1, it's not x equals to 2. And we don't have any upper boundaries here, so we keep going. Get rid of those two, and try something else. Next one is 4. Test for 4. Okay. Test x equals to 4. Good. We have 1, negative 10, 24, 32, negative 128. 1 times 4 is 4. Negative 6. Negative 6 times 4 is negative 24. You add these two together is 0. 0 times 4 is 0. 32 plus 0 is 32. 32 times 4 is going to be positive 128. Negative 120 plus positive 128 is 0. Hey, so we're lucky. We found a 0. So this test checks out, so that's 1 0 we have. And now we're going to apply the shortcut method. So we're going to take the highest power here, which is 4, and we're going to go down a power. So first we take this divisor here, and which is a factor, and go like this. X minus 4 times, okay, then put our answer, make this answer a polynomial. So we have 4, this will be 3. X is equal to power of 3 minus 6x squared plus 0x plus 32. Okay, we can get rid of this 0. Well, I'll leave it there for now. And now that we still need to bring this down to a quadratic. That's the goal, to bring the whole thing down to a power of 2. Now we're gonna keep testing with synthetic division, but this time we're going to use our test not on the bigger one, but on this one, the cube. because we already factored out the x minus 4. So let's erase this. Okay, and test for this one. I'll put this up there. Okay, we're going to test for, so we know 4 is a cube, so I'm going to mark that that's the answer. 4 is a root, and x cubed minus 6x squared plus 0x plus 32. Okay, great. Now I'm going to test the next one, 8. Test x is equal to 8. 8. Okay, you have that there. We're going to put 1, invisible 1, negative 6, that's 0, 32. Okay. I'll bring down the 1. 1 times 8 is 8. And then 8 plus 6 is 2. 2 times 8 is 16. 16 plus 0 is 16. 16 times 8 is 128. You add these together and you get 160. It fails the test. But look at this. Look at this, the answer here. We had a positive divisor, which is x equals to 8. And look at our answers. We have positive. Let's use the blue one. We have positive, positive. All of them are all positive. So guess what? It's an upper bound. So if x equals to 8 is an upper bound, then we have to do what? We have to go lower, right? We have to go down from positive 8 to a lower number to find other roots. If we go, it doesn't make any sense to go higher than positive 8 because there will be no more roots. So we're not going to go to 16, we're not going to go to 32, we're not going to go to 64, and we're not going to go to 28. It will make no sense to try test for these numbers because they won't work. They will all be failed trials. And you know, when you do polynomials, when you're trying to find the zeros of polynomial division, the divisions of polynomial, when you're trying to find the zeros of polynomial functions, it's normal to go through a trial and error process, and sometimes you go through many failures in order to derive at a root. In this case, we found only one, right? And look, wait, if 8 is an upper boundary, right, and we have to go down, we've already tested for x equals to 1 and 2, right? And if we look back at our chart here, there are no more roots to test for, right? There are no more positive roots to test for. But you know, remember we had two scenarios. Case 1 scenario would have been that we would find 3 positive roots. We went for this section here, all the positive roots. We would find 3 positive roots, guaranteed roots, or 1 guaranteed root. We found 1, but look, we can't find 3. There's no more positive roots to test. So there might be one guaranteed root on the negative side. So let's try negative roots this time. So our negative possible roots will be, and look at this number, 32. You can't go any root higher than 32. So the possible roots will only be this time -1. Leave that 4 over here. It will be -1, -2, and other roots were -4, -8, right? -16, -32. It doesn't make sense to do -64 and -128 because look at this. It doesn't go higher than 32. So just don't worry about this. Okay. So now we're gonna do this again. 8 was an upper boundary, and now we went down, and the only root left was 4. So we're gonna look at our negative roots and try this thing again. So let's test for, how about, let's choose something. How about this one, -4. Test for x is equal to negative 4. Okay? So let's put negative 4 here. And we have 1. We have negative 6 here. We have 0. We have 32. Okay? Bring our 1 down. 1 times negative 4 is negative 4. This is, you add this together, it's going to be negative 10. Negative 10 times negative 4 is going to be positive 40, right? And then this is going to be 40, and you add it together, that's going to be negative 160. And you add this two together, the answer will be negative 128. Oh, okay, so since this is not since this remainder is not 0, this test fails. It's not a root. So it's not negative 4. No way. So we're going to take that out. Not negative 4. But look at this. Although it's not a root, look what we have here. We have positive here. Positive. We have negative here, and we have positive here, and we have negative here, don't we? So this is negative, and we have alternating signs, positive, negative, positive, negative. Guess what? It is a lower boundary. This is a lower boundary. So 4, negative 4 will be a lower bound, right? Great. So this is, since negative 4 is a lower boundary, it makes no sense going lower than negative 4. And just for visual sake, if I say it, maybe some will be confused. If we look at a number line, right? Let's say this is 0, right? That's 0. Okay, that's 0. Then we have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and so on, right? It makes no sense going lower than negative 4. So if we go lower than negative 4, the negative signs will get bigger and bigger, right? Well, they seem to get bigger and bigger, but then it's getting more negative and more negative, right? So these numbers get more negative and negative. Negative 8, negative 16, negative 32, right? So we're not going to do this because negative x is equal to negative 4 is a lower bound. We don't want to go any lower than this. So we just ignore these extra numbers, and we're going to go higher than positive than negative 4, right? Which means we have to go to our next number, which is either negative 2 or negative 1. So let's go to, since negative 4 is upper bound, let's try negative 2. Okay, great. So let's erase this, right? And the number was test x is equal to, let's try this one, negative 2. Okay, we had, I accidentally erased the problem. Okay, we had 1, negative 6, 0, 32. Okay, bring down your 1, multiply by negative 2, it's going to be negative 2. Okay, negative 8. Negative 8 times negative 2 is going to be positive 16. 16 plus 0 is positive 16. 16 times negative 2 is negative 32. Negative 32 plus 32 is 0. And voila! We have a root. X is equal to negative 2. Passes the test. So we have another root here. Okay. And now we're going to look at the highest power that we had before, the highest power that we have here, because we want to make this answer into a polynomial. Make it into a polynomial. So in order to make it into a polynomial, we look at what we were dividing, a function that we were dividing, and it is, the highest power was 3. So guess what? When we make this into a polynomial, the highest power will be 2. So let's bring down our factors. There were four. X is equal to 4. We're going to make it a factor. X minus 4. Here's x is equal to negative 2, so it's going to be, the factor will be x plus 2. And in here, x was 4, 3 squared minus 8x, first power, plus 16, right? Now, can we factor this further? Yes, we can factor it further. So it will be x minus 4, x plus 2, x, it will be 4 and 4, and they both have a negative sign to it. So this will be like that. Okay, so we have these will be our 4 factors. We have 4 solutions, and our power, the highest power is 4, so we should be done factoring. But we're not quite done, right? Because look, we have 3 of the same factors, negative 4 here, and x minus 4 here, x minus 4 here, x minus 4 here. We can bring all these 3 factors that are twins, triplets together. X plus 2, x minus 4, it occurs 3 times, so it's cubed, right? Okay, and now we're done. We simplified it. We found our factors, we found our zeros, which is x. If we set all this equal to 0, all this equal to 0, solve for x, our zeros will be x is equal to negative 2 and positive 4. So those would be our roots of this long polynomial, this hard to factor or non-factorable polynomial function. Now question, can we graph this? Can you graph it? Oh yes, we have our zeros, right? Our zeros were, I'll put it over here. X is equal to negative 2. What's a multiplicity? How many times is this 0 repeated? Look at it. It's repeated only once. So it's what? Odd, right? It's odd. Of odd multiplicity, 1. This one, x is equal to, solve for x is equal to 4. How many times is this 4 repeated? Look at it. X minus 4, it's repeated 3 times, right? So it's of, this x equals to 4 is of multiplicity 3. And is that even or odd? 3 is odd. So guess what? Draw a face. We have how many odds? 2. So how many times is it going to cross over? It's going to cross over twice. Odds are strange. They cross over the x-axis. So we're going to graph this thing. The last thing we need in order to graph this function, though, now that we have our roots, we need the y-intercept. The y-intercept. And basically, if we want to intercept of something, something must be 0. And that 0 can't be y, it's going to be x. So make all the x's 0, is 0, 0, 0, 0. Now all that goes away because 0 times anything is 0. So we're going to be left with negative 128. F of 0 is negative 128. So the coordinate point will be 0 point and negative 128. Okay, hold that thought. And let's graph this thing. Okay. Remember 0, negative 128. I don't have much space here. And we're going to put a graph sign here. 0, because I'm going to forget 128. Okay. And just erase this here for even more space. Graph here. And our x-intercepts were negative 2, 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay. And our y-intercept was negative 128. So we don't have much space, so we're going to make this a negative 128, okay? Good. Now, the first thing we need to do when we graph a polynomial is look at the highest power and the sign of the highest leading coefficient. It's the power of 4, which is even. So and it's positive. So if it's even, it's gonna be up in the it's gonna be up left in the quadrant 2 and up right in quadrant 1. So it's gonna we read the graph from left to right. We're gonna graph it from left to right. The next thing we need to find out is our turning point. A turning point, or a teapot here, T and P, which is n minus 1. And the highest power minus 1, which is n minus 1, would be 3. 4 minus 1 is 3. We should have 3 turning points, up to 3 turning points. And the so it's going to be facing like this. And we have 2 x-intercepts. Okay, let's go. Our x-intercepts were negative 2 and 4. So we have negative 2 here, and we have 4 here. So remember, we started up, right? So we start up, we go down through here, to this magnet, and we stop at 2. Negative 2. Negative 2 is of what multiplicity? Odd, right? So we cross over, right? It's odd, strange, cross over. Then we go to the y intercept. Then we go straight to our next magnet, which is 4, right? 4 is of, look, multiplicity 3, and that's odd. Odds are strange, so they cross over, and we're done. That's how you graph this hard to factor or non-factorable polynomial function. You can go back and try to replay this video to understand how to graph this function, or how to find the zeros of non-factorable, hard to factor polynomial functions. And we're going to do another hard one. Okay, this question is in answer to one of our classmates' questions, and the question is how to get the roots or zeros of this particular problem. And the first thing you need to do, if you look inside the parentheses, you can factor. So let's factor it. X squared minus 9. It could be broken up into x squared minus 3 squared, which can be broken up into x minus 3 times x plus 3. All of it should be squared. Okay. Now, if we look on the right side, on the left side, we see that there's something similar. There's an x plus 3 that's similar on both sides. So what we want to do is bring the expression on the right side over to the left side. And when you bring the whole expression on the right side to the left side, it's going to become negative. Okay, now we look at those common factors again. Let's underline those common factors, which is x plus 3 and x plus 3 on that side. Okay, and we have it squared there. So what we're going to do next is take out some common factors, which is x plus 3. Good. So we're going to take out some common factors, which is x plus 3. Take out x plus 3. Notice on the left side, on the left part of it, it's squared, right? Good. And on the right side of the minus sign, it's only 1. So when we take out the common factors, 1 is going to stay and 1 is going to go. So let's break this unfactor x plus 3 squared so you can see what I'm talking about. Okay. Now underline those common factors again. Right there. Take that one out, and it's going to take this one out and send it out, those outside to the front. Okay, x plus 3. Great. They become 1. So x plus 3 times x plus 3 is inside. Remember, it was squared, now it's just to the first power. Right? 1 stays back and 1 disappears. So this one disappears. Good. It's gone. Okay. The next thing is that we have to unfactor x minus 3. So we're going to make some space on top. Okay. Unfactor x minus 3. Great. Now that we unfactor x minus 3, we have to distribute x plus 3 into x squared minus 6x plus 9. Great. So we're going to distribute the x, and after we distribute all the x's, we're going to distribute the constant of 3 into x squared minus 6x plus 9. So this x times x squared is x cubed. X times negative 6x is 6x squared. And x times 9 is 9x. Okay, now let's distribute the 3. Three times x squared is 3x squared. Three times x squared is 3x squared. 3 times negative 6x is negative 18x. 3 times 9 is 27. Okay. That's supposed to be a 7. Okay. Minus 64 equals a 0. Okay, now we need to simplify everything. Okay, we're going to look at x cubed. Underline x cubed. We don't see any more x cubes anywhere. Great. So we're going to go to the squares. We're going to put down, bring down negative 6x squared. And there's another squared, positive 3x squared. Are there any more squares? No. So bring down negative 6x squared. And positive 3x squared. Okay, now we're going to go to our powers of 1, or powers of invisible 1. And the first thing we're going to look at, I see, is 9x. Bring down your 9x. Any more powers of invisible 1? Yes, negative 18x is power of invisible 1. Okay, now we're done with those. Do we see anything else? Yes, we see we're missing a constant here. 2 and minus negative 27 minus negative 64, right? And the answer is going to be 37. Okay, great. So we have a factor of x plus 3 and this big long polynomial here, which is another factor, and they both equal to 0, should equal to 0. Now we need to simplify what's this big polynomial function. X cubed is by itself. Negative 6x squared plus 3x squared is going to be negative 3x squared. Yep. And then 9x minus 18x is negative 9x. Minus 37. So this is our polynomial here in the middle. Now, so our root would be x is equal to 3. X is equal to, we set x plus 3 equal to 0. Equal to 0. Solve for x. X will be equal to negative 3. So now the polynomial inside the parentheses, we have to try to see if we can factor it. And if we try to factor it, it's non-factorable. There's nothing that we can do. Now, we can try what we learned previously. We can do the rational root test. But just to let you know in advance, the rational root test doesn't work, right? We can try to discard this rule of signs. That doesn't work either. So the methods that we've previously used to try to get the zeros or the roots of this polynomial will not work. In order to get let me just tell you the answer. The solution for this non-factorable polynomial the answer is that x is equal to 5.71 0.60279. And if you try to put it on the graph here, you have your negative 3 here. It'll be right in somewhere here near the middle. Okay, so that will be the answer to this another x-intercept of this whole polynomial function that we tried to get. But in order to understand how to get this answer, it's beyond the scope of this video. It's beyond the scope of what we have learned so far, and that it involves basically the theory called the intermediate value theorem, or the IVT, right? And you use the IVT with something called the bisection method. But right now, well, we don't want to worry about that. And so I hope that this whole video presentation helps you helps you understand a few important things: how to get the zeros of unfactorable or hard to factor polynomial functions, right? Using the rational root theorem, the rational root tool, rational root test, and some books calls it many different things, but I call it the rational root test, right? And I hope this video helped you to understand the Descartes' rule of sign tool, and I hope this video helps you to combine the upper and lower boundary tool with the rule of synthetic division. And I hope you combine this idea of synthetic division with the shortcut method of bringing powers down from the highest powers after you divide it to a lower power that's less than one less than the higher power, and then make your answer from the synthetic division a polynomial. Well, I hope this video was very helpful for you, and I hope the best for you all in the coming weeks and months. Talk to you later. Bye-bye. You know, this is the beautiful thing about math. There are many ways to solve the same problem. And if we look at that problem again, that was asked by one of our classmates. It was x squared minus 9 squared. Okay. We have this going on here. You can also solve it in another way. Factor out x squared minus 9 to 2 factors. Well, unfactor it. Okay, sorry. Okay. Distribute 64 into x. 64x, and now distribute it again into the other term. 64 times 3 is 192. Okay, now we're going to use the power rule. use the power rule, we get this. X minus 3 all squared times x plus 3 all squared equals to 64x plus 192. Now, we're going to unfactor x minus 3 squared. You can unfactor it in many ways. Here's one way to unfactor it. Okay, x squared, right? And imagine that there's a 2 here. 2 times x minus 3. It will always be a 2. 2 times x minus 3, right? Which is negative 6x. And then negative 3 times negative 3, which is going to be a positive 9. Unfactor it. We do it again. X squared. And then 2 times x plus 2 times x times 3, which is going to be positive 6x. And then 3 times 3, which is 9. Okay, the next thing we want to do is take this and distribute it into every single term. So x squared times x squared is going to be x to the 4th power. X squared times 66x is going to be positive 6x cubed. X squared times 9 is going to be 9x squared. Okay, now we're going to do it again with this term. Negative 6x times x squared. Negative 6x times x squared is going to be negative 6x cubed. Negative 6x times 6x is going to be negative 36 squared, x squared. And negative 6x times 9 is going to be negative 54x. Let's do it again. This time we're going to distribute 9 into this, and 9 into this, and 9 into this. 9 times x squared is going to be positive 9x squared. And then 9 times 6x is going to be positive 54x. And then 9 times 9 is going to be positive 81. You don't have the space to write this, but this is what we mean. This is going to go here somewhere, okay? You don't have the space to write it. So now I'm going to look at to see which terms are the same. Okay, x to the 4th power. Any 4th powers? No, there's no other 4th powers. Okay, good. How about cubes? Here's one here. Positive 6x cubed. Another one. Yep, there's one here. Negative 6x cubed. There are no more cubes. Good. Positive. We're going to get squares. 9x squared is here. There's another here. Negative 36x squared. No more square. Oh, there's a square here. Positive 9x squared. And there are no more squares. So for this one, negative 554x. The first power. Any more x's? Yep, there's one here. Positive 54x. Okay. There are no more x's. And there's a constant here of 81. So plus 81 equals to that. Just keep bringing that down on that side. And this cancels out. Plus 9, 8 is 18. Okay, it's 18. So x to the 4th power. 9 plus 9 is 18. X squared. 18x squared. Minus 36. X is going to be negative 18 x squared. Okay, and then negative 54 plus negative 54x plus 54x is going to cancel out. Okay, and we're left with positive 81. Hey, we have enough space to put this down. 64x plus 192. Right. and we're going to put 64x and plus 92 on this side. Okay, it's going to become negative 64x plus and negative 192. We can add 81. We're going to put negative 192 together with 81. X, okay, and 192 plus negative 192 plus 81 is going to be equal to 111. Right, move this down. X minus 111 equals to 0. Okay, so we're down to this thing here. Let's erase this and gives us more space. Let's erase all this stuff up top, all this junk. And let's put this on top. X to the 4th power minus negative 18x squared minus 64x minus 111 equals to 0. Okay. Now, if we try to factor this, like we do like this, no matter what we do, it will be unfactorable. Take this out. There's nothing we can do to factor this out. This doesn't match. So we try something else. We try spinning it around. How about this one? X third minus 64. Okay. 18x squared plus. Doesn't match. Anyway, no matter what we do, no matter how we flip it and try to make it work, it's not factorable. So this polynomial is not factorable in the normal way, or hard to factor. That's one of those things. So guess what? We have to use our rational root test or Descartes' rule of sign and upper lower boundaries tools. So let's first use a rational root test. The rational root test involves us taking the constant, which is the factors of 1, 1, 1, and the factors of invisible 1 here, the leading coefficient, which is 1. And they are the factors of 1, 1, 1 are positive negative 1, positive negative 3, positive negative 37, and positive negative 111. And the factors of 1 are positive negative 1. Anything divided by 1 is itself, so you don't have to worry about that. So these are going to be our possible roots for this problem. And how many possible roots do we have? 1, 2, 3, 4, 5, 6, 7, 8. We have total 8 possible roots. That's not a lot, but we want to find out if we can shave this down a little bit more. So we're going to use our Descartes rule of signs to shave this down. So we're going to take our chart, we'll find the signs for f of x, and find the signs for f minus x. So f at x equals to x to the 4th power minus 18x squared minus 64x minus 11. Okay, and f at I'm going to put f at x here. The signs of f at x are positive, negative, negative, negative. So positive, negative, negative, negative. How many number of sign changes were there? Positive to negative. Only one sign change. So the number of real roots is 1. Right? Now we're going to do f at negative x. F at negative x, make f at x equal to negative here. Anything to an even power is itself, so it's just going to become positive. Here's even, it's going to stay the same. We put negative x here, it's going to stay the same. Here's just the first an odd power. So if you make x a negative, it's going to, this sign would change to positive, 64 x, and there's no sign here, so it stays the same. So we have f at negative x function. The signs are positive, negative, positive, negative. So positive, negative, positive, negative. How many number of sign changes are there? Positive one, or there's 1, 2, 3. 3 sign changes. So the number of real roots are 3, or an even number less than what the number of sign changes that we got. So it's going to be 3 minus 2, which is 1. So here's 1 positive roots, and here's negative. Okay? Now, how many cases do we have? Well, we have 1 positive. Case is case 1. Case number 1. We have here 1 positive, and we'll have 3 negatives. And we go up to the highest power is 4, so we're going to have 4 solutions. Oh, great. 1 plus 3 is 4, so we're going to have 0 complex numbers, a total of 4 solutions. Case number 2. Look here, 1 positive and 1 negative. 1 positive and 1 negative. That's another case that we might have. Okay, and we have 1, 2, 2 solutions. We have a power of 4, which should be 4 solutions. So there's going to be 2 complex numbers in here, possibly. So we add 1 plus 1 is 2, plus 2 is 4 solutions. And now if we look at the positive column, and if we look at the negative column, it's more efficient to go after the negative column, right? All the negative numbers, because we're guaranteed 3 or 1 real solutions or real roots. But the positive column only guarantees us just 1 or 1 real roots. So it's better to go after the one that gives us the most real roots, because the probability that we're going to find them there quicker than we will find them here. So let's first go after the negative real potential roots. Okay, and then the potential roots we have are here. Look at it. Look at this. We have 8. It's going to be shaved down by half. So our real roots will be, potential real roots will be negative 1. We're going after negatives. Negative 3, negative 37, and negative 111. These are new potential roots. And now we're going to use a test for x is equal to negative 1. And look at this polynomial here. First, we have to make sure that they're in descending order. And look, it is 4, 2, 1. But are we missing any terms? Yes, we're missing some terms. We're missing a term of 3. 4, we're missing 3. 2, we have 1, we have 0. Great. So it should be like this. X to the 4th power plus, we got to put a placeholder there, plus x, 0x to the 3rd power minus 18x squared minus 64, x to the 1st power minus 111. Good. So we're going to test for 1. X equals a negative 1. 1. The L-shaped thing. Our coefficient here is 1, 0, negative 18, negative 64, and our last number, which is negative 111. Bring our 1 down. 1 times 1 is 1. Negative 1. We're going to test for x equals a negative 1. 1 times negative 1 is negative 1. Okay. Negative 1 plus 0 is negative 1. Negative 1 times 1, negative 1 is positive 1, right? Negative 18 plus 1 is negative 17. Negative 17 times negative 1 is going to be positive 17. Negative 64 plus 17 is going to be negative 37. Negative 37 times negative 1 is going to be positive 37. Negative 111 plus 37 is going to be negative 704. So, since the root is not a 0, x equals to negative 1 does not pass, and it's not a root or a factor of this function here. So let's try something else. Let's try the next one. It's not a factor. Let's try test for negative 3. Okay. Test x equals to negative 3. Negative 3. 1, 0, negative 18. Negative 64. Negative 111, which is the last number. Okay, bring down the 1. Now, 1 times negative 3 is negative 3. Negative 3 plus 0 is 3, negative 3. Negative 3 times negative 3 is 9. 18 plus 9 is negative 9. Negative 9 times negative 3 is positive 27. Negative 64 plus 27 is negative 37. Negative 37 times negative 3 is positive 111. Negative 111 plus 111 is 0. Ladies and gentlemen, we found our 0. Since the remainder is 0, x equals to negative 3 passes with flying colors. It is a root, it is a factor. So we write down, we turn it into a factor. X, we move it to the other side, it will be x plus 3 is a factor. And then we're gonna make this into a polynomial. This is our answer. In order to make into a polynomial, we look at the highest power that we just divided by, which was this here, and it was 4. So this will become 1 less degree, 1 less power, which will be 3. Okay. X plus 3. X squared. That was 4. That's going to be 3. Sorry about that. X cubed minus 3x squared minus 9x minus 37. Just have to waste that space. 37. Okay. So now we're left with this here. Polynomial and this factor, and guess what? Our goal is to bring this thing down here, the cubed. We want to bring it down from a 4 to the 3. 2. Our goal is to bring it down to a quadratic. All right, that's our goal. That quadratic, the square. So we have to keep on finding zeros. So let's keep on finding zeros. Let's keep this in mind that we have one of our zeros is x equals to negative 3. Now we're going to find more. We tested for x equals to negative 1, x equals to negative 3 passes, and we have more to go. Okay, we're going to keep this polynomial in mind. Don't forget that one. And yeah, do more tests. Now, we had x cubed minus 3x squared minus 9x minus 37. Now let's test the next highest number, which is the next lowest number, which is negative 37. X is equal to negative 37. Negative 37. Okay. 3, 2, 1, 0. Okay. So 1, negative 3, negative 9, negative 37. Bring down your 1. 1 times negative 37 is negative 37. You add these together. Negative 40 times negative 37 is going to be positive 1,480. Okay, subtract negative 9 from 1,480. You're going to get 1,471. Add 1,471 times negative 37, and you're going to get negative 54427. Okay, you add these two together. Negative plus a negative is really negative, so it's going to be negative 554,464. Okay, this remainder is not 0, so this test fails. Okay, but look at this. We see that all of this test fails, and this is negative. We have here a positive 1, right? A negative 40, a positive 1,471, and a negative 54,464, don't we? And they're all, so we see that they're alternating, right? From positive, negative, positive, negative, and it's x is a negative, x is equal to a negative number. So this is going to be a lower bound, right? A lower bound, right? A lower bound. So that tells us that it doesn't make sense to go. We failed the test. So if we're looking at other factors here, well, which are the only ones we have left to test is negative 111. It wouldn't make sense to test that because this is as low as we should go because it's a lower bound according to our lower bound rule tool. So then we have no numbers to test. Oh, we have nothing left. But remember this. We did our when we were doing the Descartes rule of sign. We had we would either get we went after the real negatives, right? The real negative roots. We were guaranteed 3 real negatives or 1 real negative. That would have been case 1. That would have, where there would be 3 real negatives. But we can't have 3 real negatives because look, there's no more negatives to test except 1. We only have 1 real negative, and since we only have 1 real negative, that will be a case 2, right? So if we look to our left, let's go after. If we look to our left, we see there could be more real negatives in there could be real positives. There could be 1 real positive in case 2. So we're going to look for other real roots in the positive category. So let's move these aside. Okay. So we have this root here of negative 3. Leave that there because that's true. And we're going to go after our positive roots of positive 1. Not positive negative, but positive 1. Okay. 3, 37, and 111. You see, it wouldn't make sense to test for 111 because the highest that our constant goes is 37. So we're going to ignore this one and start with try to test for 1, 2, and 3. Okay, so let's test. X is equal to 1. 1, 1, negative 3, negative 9, negative 37. Okay, 1, bring down the 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. Negative 2 times 1 is negative 2. Negative 9 plus negative 2 is going to be negative 11. Negative 11 times 1 is going to be negative 11. Negative 37 plus negative 11 is going to be negative 48. Okay, this is not a root. It fails a test. So we're going to ignore that. Let's try another one. Let's try, so that 1 fails. So let's try 3. Let's test x equals to 3. 3. Let's get space here. We know this fails, so I'm going to just make space here. Okay. 1, negative 3, negative 9, negative 37. 1, bring another 1. 1 times 3 is 3. 0. 0 times 3 is 0. Negative 9. Negative 27. Okay, it's going to be 64. Okay. Alright, so x plus 3, x equals to 3 fails a test. Okay. Good. We need more space. Let's try to test for 37. This one. X is equal to 37. Let's test that. 37. Okay. 1, negative 3, negative 9, negative 37. Okay, bring another 1. 37. Okay, it's going to be 34. 34 times 37. 37. It's 1,258 minus 9 is going to be 1,249. 1,249 times 37 is 46,213 minus negative 37 is 46,176. Okay, this also fails a test. And look, not only does it fail the test, but look, it's a positive potential root. And look, all of the numbers are positive. And that tells us that this is an upper boundary. Right? It's an upper boundary. So it doesn't make sense to go any higher than 37, right? So we can go lower. Well, we can't go lower. There's no other numbers left. We can't do negative this number. It wouldn't make sense to do it. 111. Can't go any higher than that. Everything else fails. We test all of our numbers, and the only root that we got was negative 3. So if we put down what we have so far, we had this factor here. If we take x equals to negative 3, we make negative 3 go on to both sides, on the other side. That cancels out. So we have the factor x plus 3. That will be a factor. Good. So x plus 3, and we were left off with this here, times this factor, x cubed negative 3x squared minus 9x1 minus 37, which is another factor. So the factor for this polynomial here, x to the 4th power minus x squared, yada yada yada, is x is equal to negative 3. That's one factor. And this one here is not factorable, right? And now there is like I said before in the previous video, there is a solution for this polynomial, and the solution is x equals to 5.7106029, right? We'll look like on the graph, 1 2 3 here, 1 2 3 4 5. It will be right in the middle between these two points, two integers, right? But in order to understand how to get this number here, right, it will go beyond the scope of this video. It involves a theory called the intermediate value theorem. Can't spell theorem. Right? I always call it theory, all right? Theorem. There we go. Theorem, right? Combined with the something called a bisection method. Okay, you combine both of these two together, but we won't worry about this in this video. This is beyond the scope of this video and beyond what you probably will need for the class, for your class. But if you're interested, and you can just tell me, and I can make a video on this and to help you understand how to get this this point here so that we can graph the polynomial. Okay, well, I hope this helps. Take care. See you next time.